Good morning, students. So I'm Dr. V. Sudarshana Deepa from the Department of Biotechnology. So I will be dealing with the class about the chemical engineering thermodynamics. So regarding the chemical engineering thermodynamics, we have 5 units in that. The first unit comprises of the thermodynamic properties of pure fluid. In the first chapter, we will be dealing about the introduction, about the basic concepts of thermodynamics. Then we have the laws of thermodynamics. Then we will be dealing with the pressure, vapor, temperature of properties of the pure fluid. Then we have the Maxwell's relation and its application. Then we will be studying about the residual properties of the pure liquids. Then we have another chapter about the volumetric properties of non-ideal fluids. So this is the first unit which we are going to cover in the thermodynamics of first chapter. So now we will look at the universe. So the universe is fully made up of energy, and without energy the universe cannot be going, as it is impossible. So first of all, before going to the class, I would also be giving you the the founder of the chemical engineering thermodynamics. So he is J. Willard Gibbs. So he is the founder of chemical engineering thermodynamics. The books which we are going to follow for chemical engineering thermodynamics are Textbook of Chemical Engineering Thermodynamics by K.V. Narayanan. The next book is Atkinson's Physical Chemistry by Atkinson. And the third book is Chemical Engineering Thermodynamics by J.M. Smith. So these are the 3 books which we are going to follow for all the 5 units for the entire subject chemical engineering thermodynamics. So now coming to the basic concepts of thermodynamics. So thermodynamics is nothing but the study of heat and temperature. So here the heat can be measured with the help of temperature, and the study in the temperature difference is said to be thermodynamics. There are 2 types of thermodynamics. One is the classical thermodynamics, the other one is the statistical thermodynamics. In the classical thermodynamics, we will be dealing about the whole mass level, and in the statistical thermodynamics, we will be dealing about the system at the atomic level. So for all the 4 units, we will be dealing with the classical thermodynamic, and the 5th unit deals with the statical thermodynamics. Hope students you would be understanding now the basic difference of classical thermodynamics as well as the statistical thermodynamics. Now coming to the basic concepts of thermodynamics. So the first definition which you need to keep in mind before going into the subject in detail is equilibrium, the difference between the equilibrium and the steady state. So equilibrium is a state at which the conditions are constant at one particular point, whereas in case of steady state there is a constant in all the parameters where no change is observed. So the next definition which we are going to see is the basic difference between state and path. So the difference between state and path is state is said to be the condition and path is said to be the direction at which any reaction is going to take place, and the state is the condition at which a reaction is going to take place. The next definition you have to keep in mind is about the system. The system is classified into 3 types. One is the open system, the second one is the closed system, and the third one is the isolated system. So coming to the definition of the open system. So the open system is what is exchange of energy and matter takes place in an open system. So you have a container. In that container you have a solvent and a solute. So you are seeing the energy transfer as well as the matter transfer from outside to inside and inside to outside. So that is called as the open system. So now coming to the closed system. So the definition of the closed system is there is no energy change taking place in the closed system, but there is exchange of matter taking place in the closed system, which means that you take a container. So the container is closed, the container is filled with the solvent as well as the solute. So you have no energy transfer is not taking place, but the exchange of matter is taking place. So that is said to be the closed system. So now coming to the third definition of the third category, the isolated system, which means there is no energy or matter taking place, which means that you have a container. In that container you have the solvent and the solute. That container is divided with the barrier where there is no energy or no matter exchange taking place. So this is the basic classified systems which you need to keep in mind for the entire subjects which we are going to see the topics in thermodynamics. Okay. So next, coming to the next difference between homogeneous and heterogeneous system. Homogeneous system is a system where the solute or the solvent has the same properties. Heterogeneous system is a system where the solute and the solvent have different properties. So these are all some of the definitions you have to keep in mind before going to the next chapter of the basic concepts. So now we would be talking about the state functions which are of primary concern in thermodynamics. So there are four state functions you need to keep in mind which are of primary concern for the laws of thermodynamics. So one is the enthalpy, the other one is the entropy, and then the Gibbs free energy and the entropy and the internal energy. So the internal energy is given by the term U, the enthalpy is given by the term H, the entropy is given by the term S, and the Gibbs free energy is given by the term G. So in case of internal energy, the change in internal energy is given by del U, and del U is represented by the potential energy and the kinetic energy. Now coming to the enthalpy, and the change in enthalpy is given by del H. So del H comprises of the heat or the temperature difference which is taking place in a system. And now the third is the entropy, where the change in entropy is given by del S, and entropy is defined as the randomness or the disorderliness of the system. And the fourth state function is the Gibbs free energy, where the change in Gibbs free energy is given by del G, where here it is defined as the capability of the atom to move freely in a system. So these are all the important state functions which are of primary concern in the thermodynamics. So next we will be seeing the laws of thermodynamics. So all processes in the universe are considered to be under the laws of thermodynamics. The laws of thermodynamics are four. They are, first one is the zeroth law, then we have the first law of thermodynamics, then we have the second law of thermodynamics, next we have the third law of thermodynamics. So now we will be seeing the definition of all the four laws and with an example. Okay students, so now we will be seeing the zeroth law of thermodynamics. So what does the zeroth law of thermodynamics says? Two systems individually in thermal equilibrium with a third system are in thermal equilibrium with each other. So what does this statement means? Suppose you have a system A, okay? You have a system B. So A has the same temperature as B. So A and B are said to be in thermal equilibrium. We have a system with B which has the same temperature and a system with C temperature. So B and C are in equilibrium. Then we go about to say as a conclusion that A and C has thermal equilibrium. So now you can see as a pictorial representation here. So I told you as before that A is a system and B is a system and C is a system. Here A has a temperature, the same temperature B has. So they are in thermal equilibrium. Similarly, B has a temperature as same as the C. So these two are in thermal equilibrium, which is overall said to be A and C are in thermal equilibrium. So this is said to be the zeroth law of thermodynamics. Okay, students? Now we will proceed to the first law of thermodynamics. So what does the first law of thermodynamics say? Change in total energy of a system is equal to sum of work done on it and amount of heat energy transferred. So this is said to be the first law of thermodynamics. So it is designated by the change in internal energy where the heat is generated with the negative of work done. So you may be wondering the symbol, how this negative symbol came. So actually students, you need to remember a concept. Sometimes the work done will be designated with the negative sign, or sometimes the work done W will be designated with the plus sign. Sometimes the heat generated will be designated with a negative sign and heat absorbed will be generated with a positive sign. So I will give you some 4 hints how to remember the negative and the positive sign, where you have, when and where you have to imagine or remember there is a negative sign and the positive sign. So here Q, which is the heat, said to be positive when the system gains heat. Okay. So when the heat energy is gained by the system, then the symbol here is said to be positive. If the system is said to lose energy, then Q is said to be negative. Next, the work done by the system is designated by the positive symbol, and the work done on the system is said to be designated with the negative symbol. So that is why we are representing the first law of thermodynamics by del U is equal to Q minus W. So here del U equal to Q minus W, where minus W is the work done on the system. So we can also explain this first law of thermodynamics with an example. So for the daily life, how we take the food. So we take the food, energy is generated. How the energy is generated? So it is generated inside as a metabolism. So heat is generated. Then the work is done. How the work is done? The work is done by how we are walking. So this is how the first law of thermodynamics. So the internal energy is the food we take. Del U is equal to Q is the heat generated. So Q is the metabolic process which is taking place inside our body, and W is the work we are doing, walking, running, jogging, eating, whatever it is. So it is designated by the symbol minus W, right? So hope you would have understand the zeroth law and first law of thermodynamics, students, with the example. So now we will look at the second law of thermodynamics. The second law of thermodynamics states that entropy of an isolated system never decrease because isolated system spontaneously evolve towards thermodynamic equilibrium. So what does this statement mean? So example, so you have the example which is called the entropy. Entropy means disorderness. So disorderness means the disorderness between two objects. So how you can say the disorderness with the two objects? So first you take a container with the ice. So the ice is said to be the solid state. So here we know that entropy is defined as the orderliness. So in a solid, the atoms will be in a fixed form. So that is said to be, here the entropy is perfect. So when it goes to the next state is the liquid state, there you find very less, the entropy where you have little bit disorderness because it is in the liquid state. But the next stage is the gaseous state where you have more entropy, which means the disorderness is more. So this is the best example which suits the second law of thermodynamics. So now we will consider a reaction given by heat flow from surrounding at a constant pressure. So this is designated with the symbol del S surrounding, which is equal to minus del H divided by T, where del H is the change in enthalpy of the system and T is the temperature of the system at 298 Kelvin. So normally students, so what you need to be very careful here is, in all the problems, the forthcoming problems in this unit, all the temperatures will be in Kelvin. So if you see any temperature which is given in degrees Celsius, you need to convert it into Kelvin. So that is the first thing you need to look for when you see problems with the degree centigrade, because you need to represent all the temperature in Kelvin only. So now if you look at this reaction, so in this reaction, the reaction says that what is the temperature of the surrounding. So here you need to substitute the formula in minus del H divided by T. So here, so del H is said to be in this reaction 778 K and your temperature is 298 Kelvin. So when you substitute this 778 divided by 298, you get the del surrounding answer as minus 2.6 kJ per K. So this is how you calculate the temperature for the del S surrounding. So now coming to the third law of thermodynamics. The third law of thermodynamics says that the entropy of a perfect crystalline substance is zero at absolute zero. which means that the more perfect is the entropy, then it is said to be absolute zero. So before itself I told you that. So in a solid state the entropy is said to be zero, but in the liquid and the gaseous state the entropy is not said to be zero, because the disorderedness increases as in the liquid as well as in the gaseous state. So this is all about the topic under laws of thermodynamics with the examples. Okay, students? So this will be followed by the fluid flow process of a continuous process, which is based on the first law of thermodynamics. So now we will be seeing the first law of thermodynamics for a flow process. So here you have an idealist flow system where it consists of a section 1 and section 2 area. So you have a fluid flowing through the section 1, which passes through the heat exchanger Q, where the heat is converted into work Ws with the movement of the turbine, and then the fluid passes through the section 2. So the parameters when the fluid which we have to consider while the fluid when it passes through the section 1 is capital U1, which is said to be the internal energy, capital P, which is said to be the pressure at section 1, and capital V, which is said to be the specific volume, and capital Z, where the height above the determination. Then we have small u, where the velocity of the fluid is small u1. Then you have the fluid passing through the heat exchanger and then reaches the section 2, where in between the turbine is moved with the work done Ws. So here the total energy imparted at section 1 plus the total energy imparted to the field is equal to total energy at section 2. So what we are going to do is, we are going to first take the terms for the section 1, which consist of the internal energy, the kinetic energy, the potential energy and the flow energy. So the expressions for the internal energy is mu1 and the expression for kinetic energy is m into half u1 squared. The potential energy is m into g into ez1 and the expression for flow energy is m into p1 v1. So we are considering this as the first equation. So the second equation is the total energy at section 2. So the expressions are as follows, where mu2 is the internal energy at section 2 and m into half u2 squared is the kinetic energy at section 2 plus m into g into z2, where it is said to be the potential energy at section 2 plus m into p2 into v2 is the flow energy at section 2. So this we are considering as expression 2. Next, coming to the third equation, total energy imparted to the system is said to be m into q. Q is said to be the heat generated minus m into ws is the work done. So this we are keeping it as the third equation. As I said already before, total energy at section 1 plus total energy imparted to the field is equal to total energy at section 2. So here what we are doing is, we are going to add equation 1 and 3 and equate it with equation 2. So that is why I have designated here the equation as 1 plus 3, which is equivalent to 2. So we are going to add equation 1 and 3 and equate it to the equation 2. Here equation 1 is said to be for section 1, the total energy at section 1. So that plus the total energy imparted to the system, which is said to be MQ. So this equation we are equating with the second equation as the total energy which is imparted to the section 2. So taking the common term M outside, we are coupling all the expressions with the other side. In the second expression, we are taking all the common term M outside and we are coupling all the other expression to one side. So cancelling M on both sides, we get the equation as U1 plus half U1 squared plus GZ1 plus V1 plus Q minus Ws, which is equal to U2 plus half U2 squared plus GZ2 plus P2. Now we are taking the common terms of del U. So here we are taking U2 minus U1. Then for the other expression of kinetic energy, we are taking half outside. We are coupling U2 squared minus U1 squared plus gravitational force we are taking outside G, and Z2 minus Z1 we are coupling. Then we are also coupling P2 V2 minus P1 V1 minus Q plus WZ. So U2 and U1 can be designated as the change in internal energy del U plus half into U2 squared and U1 squared can be designated as the change in internal energy. Here we are designating as del U squared plus G is the gravitational force. The change in height in section 2 Z2 minus section 1 Z1 can be designated as del Z plus change in pressure and specific volume can be designated as del PV, which is equated to Q minus Ws, which is the heat generated and the work done. So here, according to the first law of thermodynamics, kinetic energy and potential energy are negligible. So we are making the kinetic energy half del U squared 0 as well as the potential energy G del Z as 0. So when we make this expression as 0, these two expressions as 0, we get an expression del H is equal to del U plus del PV. So here the change in enthalpy del H is equal to Q is the heat generated and Ws is the work done. So this is the expression we will get in the first law of thermodynamics for a flow process. In continuation of the first law of thermodynamics for the flow process, we will also look at the non-flow process. For a non-flow process, the change in total energy of the system is equal to the total energy in the surrounding. So total energy in the surrounding is equal to the total energy in the system, which is given by the term minus Q plus W, where Q is the heat liberated and the work gained. In a closed system, the change in energy of the system is given by the change in kinetic energy plus change in the potential energy plus change in the internal energy. So kinetic energy and potential energy, the change in internal energy is given by the expression del U. As we know, for a steady state non-flow process, kinetic energy and potential energy is said to be 0. Therefore, the change in kinetic energy and potential energy, when it is 0, then the expression term is del U is equal to Q minus W, where the heat gained by the system along with the work done on the system. So the first law of thermodynamics for the flow process is energy in the system and energy in the surrounding is said to be zero, and total energy in the system is equal to the change in kinetic energy, the potential energy, and the change in work. So you have an expression from del E surrounding is equal to minus Q plus W. So we are substituting this del U, which we had this previous equation Q minus W here as minus Q plus W. So here the change in energy of the system is equal to minus change in energy of the surroundings. So here the internal energy del U is substituted with this equation minus Q plus W. So minus of minus Q plus W gives the expression as change in internal energy as Q minus W. So the differential form of Q minus W is dou U equals dou Q minus dou W, and the first law of thermodynamics for the flow process is del H is equal to Q minus Ws. So please remember these two equations, students, because these two equations are applicable for the problems which is going to be dealt for the forthcoming classes. So you need to also derive the equation for the first law of thermodynamics for the flow process as well as the non-flow process, and the problems which we are going to deal with by applying these expressions will be dealt in the forthcoming classes. Thank you.